slides with us now.
So, okay, thank you very much for introducing me and also inviting me as a speaker. And then today I'm going to share my most recent researching. It is just published last week. So I hope, I hope to share this research with you. And then I'm quite open to questions and you can interrupt me anytime. So today's title is Baroclinic instability and large-scale wave propagation on the planetary-scale atmosphere. So I'm going to talk about the jet stream meandering. That's the main physics in mid-latitude. But as you know, jet is quite fluctuating a lot. And then this one has been a kind of a long time topic in mid-latitude atmosphere. So that's going to be the topic when we discuss about planetary atmospheres. And this topic has been really popular nowadays because this meandering of the jet seems to be strongly related with extreme weathers in mid-latitude. And as you know, the meandering kind of cause some area flooding and some area drought, for example, or a wildfire. So understanding the dynamics of a wavier jet is quite important to understand what is going on nowadays. But popular logic exists in this field. For example, maybe 40 years ago, 50 years ago, when the Arctic is quite cold, the jet was quite stable, quite maintaining its zonal jet. And then nowadays, because of the global warming and Arctic amplification, the Arctic started to warmer than any other areas. And then temperature gradient between north and south decrease, and then people say that that causes some kind of unstable situation in mid-latitude, and then jet starts to meandering quite in a weird way. And then that's the quite basic logic to rationalize the extreme weather in mid-latitude due to global warming. But suddenly I start to wonder, is it really making sense? I mean, lowering temperature gradient and then wavier jet. I never heard this kind of a mechanism in any course about geophysical fluid dynamics. I mean, observationally, maybe this one, could be observed, but however, in terms of fluid dynamics, I don't understand it at all. I mean, that's going to be topic in this talks. So before going further, I mean, we have to summarize the main dynamics in mid-latitude. I think most of the people are quite familiar with this concept, Baroclinic wave life cycle. I mean, this one is shaping the mid-latitude variability, especially low-frequency variability. If I summarize this one, this Baroclinic wave generated from surface by Baroclinic instability, and then propagated upward. And during this time, the pole, the heat flux is generated. And then near the top of the troposphere, this wave starts to migrate toward the equator world, and then reaches some critical latitude. And then wave breaks, and then momentum flux is generated on the upper level, and then giving energy back to the mean flow. And then this whole process could be understood by the development of the storm and decay. Here, kind of we could observe the frontal dynamics. And then this process also could be understood by the energetic diagram, which is really famous in mid-latitude dynamics. Some zonal mean available potential energy is converted to Eddy available potential energy by the heat flux, poured heat flux, and then available potential energy converted to Eddy kinetic energy. And then this one is converted to zonal mean kinetic energy by momentum flux. And then this one again goes to the available potential energy. And then this branch belongs to some lower level process. The other branch belongs to upper level processes. And then the accumulating this wave life cycle could be represented as a low frequency in the large scale atmosphere. And then this low frequency could be represented by a lot of indices. And then especially, I just want to focus on southern hemisphere because it is almost zonally-symmetric. So theoretically, I mean, it's a kind of a guideline or some theory. In southern hemisphere, there are two indices I want to introduce. I think everybody might be familiar. One of them is most famous, the southern annular mode. But actually, this mode is constructed from the upper level jet streams. And because of that, this index is strongly associated with momentum flux. And of course, the mean zonal wind in the upper levels. And there exists another index called the Baroclinic analog mode, which was introduced quite recently by these authors, Thomson and Woodward. And that one was constructed by Eddy kinetic energy. But in the case of this index represents some lower level processes. And then because of that, this index is strongly related to forward heat flux and eddy kinetic energies. And then interestingly, this index kind of showing the separated process between lower level and upper levels. I mean, between two indices, I really want to focus on Baroclinic analog mode because it has really strange and interesting variability. And then this is that analog mode represents BAM, Baroclinic analog mode. And then if we draw power spectrums, I mean, we could see a very clear spectral peak around 25 days. And then the reason also I'm focusing on this index is this one is related to polar heat flux, and then this one is related to precipitation in the mid-latitude. All of them shows a spectral peak around 25 days. But in the case, kind of a question exists. Okay, 25 days. This time scale is bigger than weather. Weather time scale is 1 or 2 or maximum 3 days, but smaller than the season. Normally, season time scale is around 3 months, and at 25 days exists between these two scales. Normally, we call it sub-seasonal. And then we can ask a simple question: what is causing this variability? And then this oscillation is a really regularized motion, but somehow we know that after weather scale, I mean, weather is very chaotic, and then 25 days means that we must pilot the, this chaotic dynamics and then generate some quasi-oscillation. That's very, very interesting. And then if we look at the, for the heat flux.
Excuse me, Woosok, before you go on, can you discuss a bit more the model you use? I mean, the specification of the model? Or
Sorry, the model?
Yeah, where does the data come from? Is it produced by a model? I mean, which model?
Oh, no. This one is from the reanalysis data, I think. Okay. I think they use anchor answer reanalysis data. I'm not sure about between ECMWF or anchor answer. I think and this model is quite robust in any of the reanalysis data. And then they constructed this model from the eddy kinetic energy. Okay. And then, yeah, I think this one is a kind of a first mode of UF analysis. Okay, and then this one is a correlate, quite related with vertical polar heat flux and then precipitation. I mean, if you look at their science paper, they summarize the data analysis quite clearly. Okay, it is from the data. And then it is from the also, this one is anchor answer reanalysis data. I draw it. I really wonder how this polar heat flux is looking at in spatial domain. I mean, if you look at that, x-axis is day numbers, and then y-axis is latitude. I mean, it's a southern hemisphere. And then if you look at the heat flux itself, it shows a quite low frequency variability. I think if we draw in power spectrum using this one, I mean, we could find that spectral peak around 25 days. Okay, so now the question is like that. I mean, as an applied mathematician, I really want to derive a stochastic oscillator. But in the case that we have to use a primitive equation and then use some approximation. But in the case of what kind of equation do I have to rely on? And then this time scale lies on between season and weather. And that was the fundamental question I can ask. Low frequency exists. And then in that time scale, there exists some extreme weather caused by wavier jet. Also, some interesting variability, quasi-oscillatory behavior exists for the heat flux. But in the case of what kind of equation do I have to rely on, that was my first question for these problems. But in the case, I have to do shopping around some historical models. I mean, first one is, as you know, from the climate 101 class, a climate model, it is the basic GCM. I mean, we just see Earth as a point object in the universe. In the case that what we have is energy flux balance, right? Incoming is equal to the outgoing. So incoming solar radiation should be balanced by outgoing long-wave radiance. What we could get is average temperature of the Earth. And then if we magnify the Earth, in the case we could realize that heat flux imbalance exists reason by reason. Especially in tropics, there is a surplus, and polar area, there is a deficit. And then by a simple physical guess, we could guess that the heat transfer existed from tropics to the polar area. But in the case, main equation could be forced heat equations. In the case, this diffusion term represents the kind of sum of all synaptic vortex activities right here. Even though that's very chaotic and complex, eventually that one exists to transfer the heat from tropics to the polar area. And then what we have, we just magnify the Earth more, we could focus on the mid-latitude right here. The major dynamics is vorticity dynamics. And the main equation becomes quasi-geostrophic potential vorticity conservation. And then out of that main physics is Baroclinic instability and Baroclinic wave life cycle. But in the case, I just put these models right here in one place. And then in the left-hand side, there is the energy flux balance. Maybe time scale at least the seasonal, because maybe this forcing is essentially seasonal from external source. And then on the right-hand side, there exists a quasi-geostrophic potential vorticity equation. Time scale is 1 or 2 days. But what we are looking at is sub-seasonal time scale, which is around 20 days. It should exist between these two sides, somewhere right here. And then I have to ask a question, what kind of equation do we have to rely on? It is a quasi-geostrophic equation, but in the case, the time scale is too short. And then this, just a heat flux balance, but in the case, there is no dynamics. And then my fundamental question starts from here. I mean, what is the main equation to represent the low frequency in the large scale hemisphere? So now, again, I will go to the real basic, the basic scaling. Scaling of the magnitude of the jet streams in the middle latitude. I mean, it is a really basic one, right? We have to use a geostrophic balance right here. But then a little bit manipulation by assuming that this meridional gradient of the pressure is the same order of the meridional gradient of the temperature. And then U should be scaled by meridional temperature gradient. And in the case, the U is around 30 meters per second by this scaling. And then I want to introduce one scalar, some long-dimensionalized small number alpha. That one is representing meridional temperature gradient. In the case that this scale of the U is going to be represented by alpha. And then, as you know, the most important non-dimensional number in large scale hemisphere is Rossby number. And then Rossby number should be related to the alpha. It is the kind of a relationship between dynamics and thermodynamics. And then this expression, interestingly, could be represented by this way. Some L squared over LD squared epsilon, that is the alpha. And then LD is defined by square root of GH over F. That is, the meaning is external Rossby deformation radius. In the Earth, it is 3,000 kilometers. But in the case, interesting happens. Large scale hemisphere, we know that it is beyond the 1,000 kilometers. And then normally 1,000 kilometer means kind of internal Rossby deformation radius in the atmosphere. If L is 1,000 kilometers, I mean, we can choose the length scale, it's our choice. And then if we choose this one, and then L squared over LD squared in the Earth is becoming around 0.1. And then epsilon is, let's assume that it's around 0.1. In the case, alpha is the order of epsilon squared. However, if we choose a length scale is similar to LD, or Earth radius 6,000 kilometers, but in the case, alpha is same order with epsilon. What I want to say is that alpha should be scaled differently depending on the choice of the L in large scale hemisphere. And then we could see kind of two asymptotic limits, which means, which might imply there exists two scales in the large scale hemisphere. So, I mean, let's do basic scaling. I mean, it's from the Pedlowski's book, fluid dynamics, and then under the assumption that alpha has some specific order. For example, here, if the alpha is in order of epsilon square, we could do some long-dimensionalization and regular perturbation analysis to derive the asymptotic equations. But in the case of what we could get is leading order is geostrophy and hydrostatic balance, and geostrophic degeneracy exists. So we cannot close the main equation, so we have to go to the higher order. In higher order, vorticity dynamics comes out, and the final equation becomes a quasi-geostrophic potential vorticity equation. That's the basic one for the Baroclinic instability and synaptic wave life cycle. However, if alpha is in order epsilon, in the case of different equation set comes out. But in the case we don't need a higher order, in the leading order, equation set is going to be closed. Interestingly, the continuity equations, here there is the beta effect. In the case that we cannot treat beta effect is in higher order. In these scales, the beta effect is order 1, and then we can derive a Sivador relationship, which is a quite key relationship for ocean dynamics. Even in the atmosphere in planetary scale, this relationship should be maintained as a leading order dynamics. And then heat equation also survive, and then this heat equation becomes the leading order equations in this scale. The planetary geostrophic motion, I'm not introducing this one for the first time, and for a long time ago, one was suggested. For example, Berger criticized the Chinese paper because the Chinese paper title contains the long wave, and then Berger criticized the Chinese scaling, saying that the other scale existed, and that one is a planetary geostrophic motion. And then Phillips also mentioned this one, and then Phillips said in his review paper, geostrophic motion has two kinds. And then he said planetary geostrophic motion is called geostrophic motion type 2. Okay, so this one is not introduced by me. The other guys introduced this one. But and then what I want to say is that these two scales coexist in large scale atmosphere, and then we can assume that they are interacting. And the case question is how to represent that interaction. Because of the two scale coexisting, I can use the multi-scale formulas. But in the case, I have to introduce two coordinates, one for the planetary scale, the other for the synoptic scale. And then, just the regular, multi-scale, analysis. And then in the case, the important thing is it's a scalar. L over LD is epsilon half. Okay, this scalar comes from this ratio. And the key assumption is that the thermodynamic variables has three components. One is average vertical profile, and second is a contribution from the planetary scale, and then the other one is a contribution from the synoptic scale. Under this assumption, we can do kind of a boring, this scale analysis and then perturbation analysis. It is just an example. I just wrote down the Navier-Stokes equation based on this multi-scale formalism, and then we can arrange that order by order. And then finally, I'm not going to go into the detail of this process, but finally, I can introduce a closed equation containing the two scales and their interactions. I mean, first of all, in the dynamics, both of them satisfy basic balances, geostrophy, hydrostatic. And the planetary scale satisfy the Sivador relationship. And then in the heat equation, their interactions comes out. On the left-hand side, you can see that the time change of a planetary potential temperature and advection of the potential temperature, that is forced by some synoptic scale dynamics and plus external thermal forcing. And in potential vorticity equation, if you look at that, these planetary variables, planetary wind field is acting as a mean field for the synoptic vorticity dynamics. This is the closed equation representing the interaction of the two scales. So now we are we are doing some research about the low frequency in the atmosphere. Because of that, we have to focus on planetary scale equation. But we cannot ignore the interaction with the synoptic scale. Synoptic scale is acting as a forcing. The main equation is a heat flux balance equation. And then here, the synaptic scale provides the heat flux convergence for the time change of a planetary scale potential temperature. And then here, I mean, I have to do some temporal and spatial averaging. Somehow later, I have to parameterize this heat flux convergence by planetary scale potential temperature. If I do temporal and spatial averaging, and then especially this synaptic scale derivative is converted to planetary scale derivative with epsilon half scalar by spatial averaging. And then in these equations, this bar is temporal averaging, and then epsilon half planetary coordinated derivative coming from the temporal and spatial averaging. And this is going to be our main equation to investigate the dynamics in planetary scale. Because of this scalar, we could think of some regular perturbation. So theta L is represented by leading order plus epsilon half order dynamics. But in the case, what is the leading order and what is the half higher orders? If we invoke a leading order under the assumption of zonally symmetric planetary scale atmosphere, but in the case of because of a zonal symmetry, the meridional velocity and vertical velocity will be zero, negligible. So essentially, these velocities should be in the higher order, epsilon half order. So main equation is just a geostrophy and the relationship between the temperature and the pressure. And then this is the main equation. Time change of the potential temperature is forced by external thermal forcings. For steady state, so this one is going to be erased in the case that QL, the theta SL should be zero. I interpret this one is a radiative convective equilibrium in a local region. I mean, we could calculate the radiative convective equilibrium in the case that we will get radiative convective equilibrium temperature. That's going to be theta E. And then this theta E is going to be used to find mid-latitude zonal mean velocity structures. I mean, as you know, Held and Suarez introduced this concept. And then this setting is popularly used for idealized GCM core simulation under zonal symmetry. But then next order is going to be perturbative equations. And then this one actually contains the heat flux convergence from the synaptic scales. And then left-hand side is the temperature, potential temperature evolution in planetary scales. And then plus we have a Sivadova relationship. These two equations are going to be main equation. And then the main question is how to parameterize synaptic heat flux. The simplest parameterization might be Fickian approximation. If we write down the flux equation, normally first thing we could think of is a Fickian approximation. This flux is proportional to the gradient of the mean field. And then we are going to introduce a diffusivity K. But in the case, main equation becomes probably diffusion equations. But however, it needs a very strong assumption that the time scale for the eddies should be much, much smaller than the time scale for the mean field C. But normally in turbulence case, it is not the case, right? The time scale of the eddy might be comparable with the time scale of the mean. I mean, here we have a time scale separation, but that's not that much. So in the case that we have to care about the time change of this flux too. I mean, it is a typical turbulent closure problem. And the simplest one is called the minimal tau approximation. This one was introduced 20 years ago in dynamo field, the Blackman field, and then Brandenburg also tested this turbulent closure scheme, minimal tau approximation. So minimal tau approximation is simply explained by these equations. Here, if we do turbulence closure problems, this time change of a second order moments we shouldn't need a third order moment on the right hand side as a forcing. But somehow we have to cut off. So here assumption is all of the other terms into this gradient terms acting as a damping of second order moment. That's the minimal tau approximation. If we introduce this scheme, in the case, the main flux equation becomes a damped wave equation instead of the parabolic heat equation. But then if you, I'm not going to go into the detail, this scheme is used for forced turbulence experiment. Here, Brandenburg et al. Kind of introduced the quality of this approximation, and then which is quite good compared with the Fickian approximation. And then Manucharian and Sper 2016 and 2017, I mean, they also introduced a minimal tau approximation to rationalize some oscillatory behavior in ocean circulation in multi-decadal timescales. I mean, I'm not going to go into detail, but if you look at those papers, you can see the advantage of minimal tau approximations. This minimal tau approximation also used to explain that the quasi-oscillatory behavior of the BAM index that is in our previous paper. I'm not going to go into the detail, but we derived the stochastic oscillator from the planetary heat equations. And this is the comparison. This thick line, this one is a power spectrum of the BAM index from reanalysis data, and then the others are coming from the stochastic oscillator model. And then this stochastic oscillator behavior is well represented by that minimal tau approximations. And then this minimal tau approximation could be interpreted as Eddy memory effect. That differential form also could be represented by integral form. In the case, we can interpret in this way. The current heat flux is the result of accumulating the past mean status. So, I mean, that effect of the mean status is going to be controlled by this integral corner. I mean, here for minimal tau approximation, we use the exponential corner. And then here R is going to be represented by Eddy memory size. And then this R is going to control the how much it piled up existed from the past. So if we apply this more generalized parameterizing for the heat flux, our main equation has three equations. One is a heat equation, and the second is a parameterization, the Eddy memory effect. But in the case of time, the derivative is interpreted as advection by mean barotropic wind. And then the last equation is a Sibodorov relationship. And then I want to put the typical boundary condition for rigid boundary. So vertical velocity is going to be 0 at the surface and also on the top of the atmosphere. I mean, that's going to be modeled to represent the large scale, planetary scale atmospheric dynamics in Baroclinic atmosphere. So now, for simplicity, I want to introduce a two-layer format. I mean, that's the simplest one. And then I take another z derivative. That's just a technical convenience to put this equation into these two layers. I mean, without it, we might need 3 layers. But after doing this one more time z derivative, I can put this 3 equations into 2-layer settings. And then for the process, I mean, we needed to deal with the Sibodorov relationship first. I mean, I'm going to use a very specific form of the vertical velocity. That this one is automatically satisfy the boundary conditions for W. But however, same thing is going to be derived by finite difference method using this coordinate. But anyhow, after assuming this specific form, I mean, we could find the W0 by Sibodorov relationship, and then that one is going to be represented by the main variable Q. And then Q is of z derivative of potential temperature. But and then after doing this one, we could write down main equation like that. This is a 2-layer and an Eddy memory effect. The here important parameter is P. I mean, that one is a kind of size of a Sibodorov relationship in each layer. And then that one is a proportional to beta, and S is a dry static stability. And then, automatically we do algebra. And then this is the main equation after combining Eddy memory effect, and then we can do normal model analysis, quite typical one. After putting this in normal form, we could find the characteristic equations. And the characteristic equation represented by force order polynomial equation. if you look at this form, I mean, especially on the right-hand side, this guy, P delta U minus 1 over 4 delta U squared, that sign is going to be quite critical. And then, for example, this one is, okay, one case, this one is positive. This one is positive means that delta U, that is the shear, the difference of the velocity between upper level and lower level. If shear is smaller than 4P, a threshold, but in the case, we could find a 4 mode, sigma 1, 2, and 3, 4. And then A and B just shows 2 cases with a different R, and then I use some values. I mean, we can do a lot of, we can do investigation on a lot of cases, but I just want to introduce this one. So A is, R is 0.25, which means quite short eddy memory size. But in any case, the real value of the sigma is proportional to growth rate of the eddies, and then the imaginary part is related to the phase velocity. If you look at the growth rate, as k is increasing, these guys become positive right here, which means there exists instability. And the more interesting thing is, if you look at the phase velocity, especially sigma 1, it becomes almost 0. Almost 0 means that this mode is almost static in that area, not moving much, and then growing in time. That's the kind of case here. And then the other case, if the memory is a little bit longer, in the case this case disappear, and then all of the phase velocity seems to be 1, and the 1 is the same as mean barotropic wind, which means that the perturbation just follow with the barotropic wind and then grow. So interestingly, here the main point is the baroclinicity, the delta U, is smaller than some threshold. In the case of some instability, new instability exists. And then for some parameter space, that mode could be quite static, very stationary, and then growing in time. The other case, if the shear is bigger than a threshold, that instability disappear, or mode just decay in time. And then definitely a lot of phase velocity appear, but I mean, in this case, that instability disappears. Interestingly, unlike synaptic scale, in the planetary scale, the Baroclinic instability existed, but this instability needed optimal shear, optimal vertical shear, instead of the large vertical shears. So when the shear or the meridional temperature gradient is lower than some value, in the case, instability exists, which is quite different from Baroclinic instability in synaptic scale. Okay, it is just from the some characteristic calculation, we have to interpret this one in more detail. For example, here, what is the role of the eddy memory? I mean, we have to know what kind of role exists in eddy memory. The eddy memory means some kind of way of interaction between synaptic scale and planetary scale. But in the case, let's assume what would happen if there is no memory? But in the case, our main equation, I mean, here, instead of the Q1 star, we are going to use a Q1. In the case that it is just the Fickian approximation, which means no memory exists. And then we can do normal mode analysis again, but still that planetary scale instability exists. However, phase velocity is always fixed as U bar, the mean barotropic wind. So without the memory, or perturbation just to follow the mean wind and then grow or decay. What I want to say is, without the eddy memory, it is impossible to find unstable, almost neutral waves propagating against the mean wind. I mean, it is not realistic. If we look at the atmosphere, large scale atmosphere, some planetary scale waves could move westward or eastward with respect to the mean wind. So to generate such wave by interaction of two scales, we need eddy memory. Without the eddy memory, that doesn't exist. And what is this instability? Requiring some optimal shear instead of the large shear. I mean, here main dynamics is simple, just a heat equation and Sivadov relationship. So just the heat equation, and for example, just the shear is a pure shear case without the Sivadov relationship, we can write down main equation like that. But in the case the main equation using barotropic mode is just a simple wave equations. In the case of two kinds of wave propagating westward and eastward with a velocity delta U over 2. If we include a Sivadov relationship, I mean these factors, in the case the main equation has additional terms which represent contribution of the Sivadov relationship. And then you can see that this Sivadov relationship is decreasing the wave propagation speed. Right? Initially, without the Sivadov relationship, the speed is delta U over 2. However, with the inclusion of the Sivadov relationship, that speed should be decreased. However, if this guy is bigger than the 1 over 4 delta U square, this main equation is no longer wave equation. It represents the growth of the mode Q bar. I mean, that's the instability. So the effect of the Sivadov relationship could win over the effect of the shear in the case that this instability starts and then perturbation grow in time. So this instability comes from the competition between the shear effect and the Sivadov relationship. And when the Sivadov relationship win over that, and then this Baroclinic instability initiated. And then next is kind of in this characteristic equation, activity of the synaptic eddies is represented by one constant, eddy diffusivity, right here. And then this term is quite important. If you look at this characteristic equation, if this quantity is positive right here, the phase velocity is going to be just U bar, following the mean wind. I mean, to observe some planetary scale waves propagating differently from the mean wind, we need to see that this quantity should be negative. In the case, we need some magnitude of large K. So, which means the effect of activity of the synaptic eddies is necessary to generate the planetary scale waves propagating against the mean wind, which is critical. I mean, that one could be seen in this simple characteristic equations. So now, I mean, after introducing this new instability and then role of the interaction between two scales, I have to go back to our initial argument, initial problem, the wavier jet and global warming. I mean, 10 years ago, I think this research is kind of a starting point. Francis, they argue that increase of extreme weather is closely related to decrease of the meridional temperature gradient, mainly caused by Arctic amplification. And then they say that temperature gradient decrease, that one just caused the wavier jets. But however, this research was based on observation data analysis. But in the case that quite typical criticism could come out. One criticism is definitely the length of the data. It's not able to make some strong conclusion, right? And then the other criticism is, lack of a theory. How could you rationalize that argument? I mean, these two criticisms just come out. But then this research is quite interesting. I mean, they tested their idea using idealized GCM. But in idealized GCM, they could not observe the increase of frequent occurrence of atmospheric blocking under the Arctic amplification. Decreasing temperature gradient does not guarantee the increasing frequency of atmospheric blocking in the simulation. So let's rationalize their argument using this our characteristic equations. I mean, if we look at this one, as I explained before, to observe blocking like a disturbance in planetary scale, we need this condition to make this one imaginary numbers. So we need some large K somehow, right? So however, this K to this, the Bay 2002 research, they kind of find the scaling of synaptic heat flux by meridional temperature gradient. According to their research result, I mean, we could say that this large K is proportional to the meridional temperature 3/5, which means to satisfy these conditions, we need some large Ty. But to provide this planetary instability condition, we have to decrease the Ty. So competing factor exists. For the blocking-like disturbance, we need the large Ty. However, for the initiation of the Baroclinic instability in planetary scale, we need a small Ty. So because of that, I mean, under the condition of decreasing temperature gradient, we cannot guarantee that we could see lots of blocking-like disturbance in the large scale atmosphere. Maybe it is the kind of a rationalization under this simple model. And then again, I mean, we have to mention about this criterion for instability. I mean, that criterion represented by 4P, and then that is proportional to beta and dry static stabilities. So recently, there is research saying that the jet stream in the Atlantic section moved forward under global warming, which means that beta is decreasing. And other researching, the Frears in 2006, say that under global warming, dry static stability increases. Again, competing factor exists somehow in the case that we don't know how this criterion change under global warming. I'm not sure right now until now. But if this one is bigger, it is better for the instability. If it is small, it is hard to generate that condition for instability. So anyhow, what I want to say is that the under global warming, what would happen exactly, is a bit complicated question, even in this simple model. Okay, so I just want to make a simple conclusion out of this presentation. I mean, first, I introduce multi-scale formalism. And the multi-scale formalism means large-scale atmosphere is going to be represented by a combination of the two scales, planetary geostrophic motion and quasi-geostrophic motion. And in the case, I just want to interpret this one as wave-mean interactions. Wave means synaptic eddies from quasi-geostrophic dynamics. And then mean is provided by planetary geostrophic motion. And then this multi-scale formalism could be interpreted as wave-mean interactions. And then I hope this formalism could be used for further research about low-frequency dynamics in planetary atmosphere. And then I have to mention that, I mean, from the first, nowadays, the wavier jet is the main focus, generating a lot of extreme weathers in the Earth. But in the case that this one could be one mechanism to rationalize that one. Arctic warming and decreasing the temperature gradient, meridional temperature gradient. And then that one provides the better condition for the planetary scale Baroclinic instability. So maybe this better condition could be one reason for the frequent happening of extreme weather nowadays, even though we need further research about that statement. But under this theoretical research, I mean, we could mention this possibility. And finally, I mean, it is about the further research. Right now, I assume that zonal symmetric condition. But however, for example, in Northern Hemisphere, zonal asymmetry is quite important. Then this contrasts the orographic forcings. And then this one is ongoing research right now. I mean, we investigated how the planetary geostrophic motion respond to zonally asymmetry surface thermal forcing. I mean, interestingly, in this research, we also see threshold behavior, and that threshold is also defined by beta effect and static stability. And then this U bar is barotropic wind. If this barotropic wind is smaller than a threshold, in the case planetary geostrophic motion respond quite bigger. The bigger response is expected. And it might be related to wavier jets also. But however, to complete the research, what we need is kind of this planetary field should interact the field. synaptic eddies, which means that synaptic eddy should be generated by Baroclinic instability by this field. But in the case of what we need is generalized Baroclinic instability problems. So non-zonal Z Baroclinic instability. That one has not been done, and that could be a good topic for further project. So somehow, okay, the last sentence I can say is that the new instability I introduced here is could be used to support the idea that the global warming might be causing some extreme weathers in mid-latitude. I mean, this instability might be preferred nowadays due to the ongoing global warming. But even though we need further investigation, I mean, this one could be some guideline for further research. That's my hope. Okay, I mean, that's my last sentence. Thank you very much for coming to my presentation.
That's great. Thank you so much. Are there any questions?
Mm-hmm.
While you're thinking of questions, like maybe I can ask the first one. So I suppose I was wondering if I mean your model is really interesting. Have you tried to fit any of the parameters in it based on observational data? So I don't know, trying to do a decomposition of kind of observational flow fields into this planetary scale and the small scale geostrophic and so on.
Right now, I mean, first thing we are doing is, I mean, here, here kind of, the parameterization, Eddy memory effect. This is our main focus. So in the case, kind of, we just rely on minimal tau approximation because it was introduced before in dynamo theory, and then we trust the quality of parameterization. And also in previous research, it shows the quality of parameterization. However, what we could do is, where is that? Generally, in this present, you can see that this integral forms. What we are doing is here, this, I already explained that this integral corner exponential one. I mean, this one is the key to define the past memory effect, right? So what we are doing is let's construct this integral corner from the data. That's what we are doing. Okay, if I say just a result, I mean, it's very similar to this one, finite memory one. However, there exists some, imaginary part right here. Some oscillatory part exists. If I use observation data and then try to construct this integral corner, and then some oscillator part exists. And then also, we also try to find some dynamic reason why that kind of oscillatory part exists. But what I want to emphasize, even with that oscillatory part, the main result is not going to change. Okay, I mean, that's what we are doing. But the further research about planetary scale motion and matching it, the data, I mean, that one should be done in the future. That's going to be quite interesting.
Great, thank you. We have a question in the chat. Would the person who posted it like to unmute themselves and ask it?
Okay, I mean, that's quite a good question. Kind of he mentioned that the width of the boundary of the jet, I mean, width is quite small. Yeah, actually that's true. But what I want to say is the jet is observed in the upper levels, and the jet could be quite sharp. Normally, that one is done by momentum fluxes. But here, the momentum flux contribution is ignored because it is in higher order. So in this formalism, what I assume is kind of the length scale for the X and length scale for the Y is almost equal. I mean, to represent that kind of a width effect in meridional domain, I think we have to use a different length scale for the X domain and Y domain. I have not tried that one. Okay, that's what I can say. And then important thing is here, because I rely on the heat equation in the planetary scale, the moment flux effect is not considered because it is in the higher order. If you look at my previous paper, I explained it quite in detail.
Could I come in, Hannah, please?
Oh, yes, please do.
If there is any question.
Yeah,
Yeah.
thanks very much, Woosok. Very interesting talk. Just wondering about your plans for future studies. With a two-level model, you can't really see any influence of the stratosphere. So I was wondering if in the future you would think of having a more highly resolved model where you could look at stratospheric influences perhaps.
Yes, I mean, that's a really good question. I mean, the further direction of this research, I mean, definitely we can rely on the two-layer models first, and then do nonlinear simulation to see the nonlinear effect. Right now in my research, I only shows the initial development of a planet-scale disturbance in the two-layer. And then we can do further research in this layer model to see the nonlinear effect. And like you said, I mean, definitely we have to move to more, some refined model. For example, GCM, dynamic core. In the case, we could construct some non-zonal jet field with some, specified forcing, and then we could run this model to see how synaptic waves develop from the non-zonal effect, and then see how they are interacting. So, I mean, that one could be designed. I mean, we are thinking of that. I'm going to use a dynamic core first to see the dynamics clearly, and then to define the interaction between two scales more clearly. I mean, definitely we are going to do that. And also, I mean, because you said the stratosphere effect, I mean, that's one of the topics we are focusing on, especially we are caring about the downward propagation from the stratosphere to the troposphere. We are kind of doing some investigation about it. We think that it could be explained by Eddy memory effect in terms of two-scale interactions. I mean, that's what I could say. I mean, definitely we are thinking of that.
Yeah, good.
I mean, any question is okay.
Could I just come in again, Hannah, please?
Yes, please.
Are you familiar with the work of Peter Lynch, who worked on planetary scale, non-geostrophic planetary scale baroclinic instability? Many years ago, he wrote his PhD thesis on this, and it was published back around the early 80s, I guess. But maybe, are you familiar with his work at all?
Honestly, I'm quite new in this field, so
Yeah.
maybe because of that, I failed to collect all the previous work. I mean,
Yeah.
unfortunately,
You might keep an
if
eye
you
out.
give me that name, I will look into that.
Peter Lynch, L-Y-N-C-H. Peter Lynch.
Okay, I will look into that. I mean, that's. I thank you very much for giving me that information. I mean, I'm really tracing down the history of this planetary geostrophic motion. Thank you.
Great. We have a question in the chat. Says, thanks for a good presentation. I'm a PhD student at SNU. I'm not sure I understand it correctly. Thus, my question might be silly. No concerns. There are no silly questions. Some papers try to investigate the blocking formation using quasi-geostrophic energetics. Can you combine your concept with energetics?
I mean, definitely it's a quite important question because, I mean, in this simple model, I kind of ignore the detailed dynamics of QG eddies. And then I just only use the memory effect plus diffusivity K. And then I just use these two quantities to represent the interaction. But however, in reality, the QG eddies have a significant role. I mean, definitely I also emphasize that. And then also very showing the very complicated features. And then maybe energetics could be used to represent that complex interaction between synaptic scale and the planetary scale. But in the case what I could rationalize this one right now, I mean, for the related to this issue, I mean, here I use the 2-parameter Eddy memory size R. I mean, I think the short memory is necessary. But what I'm guessing is this short memory means explosive cyclone development. And then some papers suggest that explosive cyclone development seems to be the indicator of the atmospheric blocking. But I'm not sure that relationship exactly right now. And then the logic large K, which means synaptic waves interact with the planetary scale quite a lot. That one is going to be represented by a large K. So maybe the detailed dynamics of huge eddies in this planetary atmosphere should be understood to find the relationship between the complex behavior of huge eddies and eddy memory and diffusivity. I mean, I don't know exact relationship right now, but further research should be done to find out that relationship. It's a kind of a, it's just a simplification, too much simplification of that complicated picture. So in the case, I mean, to use this one for more realistic atmosphere, I mean, we need to find out that relationship. I mean, that's going to be my answer. Yeah.
Great, thank you. Are there any further questions? If not, I think we can all thank Woosok for a wonderful talk, and we finished right on time. Our next seminar speaker is actually to be confirmed, but will take place on the 1st of February at one of our normal time slots. So please keep an eye on the website and the mailing list for further details closer to the time. So a virtual round of applause for Woosok, and many thanks again for your talk.
Thank you.